Hi, my name is Mona Abraham and I'm doing a post-quiz tutorial on gravitational force. I'm looking at Chapter 3, Problem 36. And the problem is discussing a spacecraft and that we have here called a near spacecraft and its interaction with an asteroid called Mathilde. The spacecraft is traveling at 10 kilometers per second and it gets as close as 1,200 kilometers to the asteroid. And the question is asking the effect the asteroid has on the spacecraft here. So the first part of the question is asking to do a rough diagram of the effect on the spacecraft, which is a good way to start most problems. So I started by doing a force diagram. Here you can see that the gravitational force is in this direction, which is the negative unit vector r also, and the spacecraft is traveling at a velocity at this direction. Next, the problem asks if we can estimate the change in momentum of the spacecraft that would result in the encountering with the asteroid. So to do this problem, I focused on Newton's gravitational force and took this formula. F grav is equal to negative g m1 m2 over magnitude of r squared times the unit vector r, and applied it to the spacecraft, and I made sure that I kept my units in, I kept it in SI units. So from here I needed to find the mass of the asteroid because that was not given. I was able to find the mass using the density and the volume, which were both given in the problem. Again, units was really important to make sure you keep it in meters here, and so between those two values I was able to find the mass, and after that I was able to calculate F grav. So from there I applied the momentum principle, which states the change in momentum is equal to F net times delta t. Since the force of gravity is the only force being applied to the spacecraft, that's the only force we need to take into consideration. So in order to apply this formula, it's necessarily that we calculate delta t, and we're going to calculate delta t using the r value that they give us and the initial velocity. And in order to calculate the velocity, it's distance over time, manipulate the formula, and you can get time is equal to distance over velocity, and again, units, seconds. And then from there, we were able to calculate the change in momentum using F grav from the previous sheet and the delta t that we just calculated. And here, as you can see, units come out correctly. The next part of the question asks us to determine the distance of how far off course the spacecraft would be after one whole day. And so in order to do that, we again apply the momentum principle. P equals delta P equals m delta V. And we can use this formula to approximate the momentum because the velocity that we're using is a lot smaller than the speed of light, so we can go ahead and use that formula. From there, we manipulate the formula in order for us to determine what delta V is, and we calculate delta V by plugging in the numbers, and then from there we use again this same formula we used up here to calculate delta R. And we get 253.152 meters. Also, to calculate delta T, we had to convert 24 hours to seconds. So it's making sure that you pay attention to the units you're using. Next, the question asks, well, the question states that the scientists observed that the asteroid was a loose arrangement of rocks and with lots of empty spaces inside, and it's asking how these scientists came to this conclusion. So, scientific conclusion. The calculated delta R was 253.152 meters, but what they expected R to be was a lot less than that. So from that, we can conclude that the mass of the asteroid that we calculated had to have been greater than what is expected, and then thus from that we can conclude that the density that we were given is a lot bigger than what the actual density is. And finally, we can conclude that there is a loose arrangement of rocks, which would definitely contribute to the reason why the density is significantly smaller, mass is significantly smaller, delta R is significantly smaller.